Right, so what I'm going to talk about today is joint work with Misha Rudnev and Ollie Roche-Newton. I took the opportunity to go to their websites and fetch some photos. Here they are. And perhaps unsurprisingly, given our interests, this is a talk about questions related to the Erdos-Szemeredi sum product problem. So to set the scene, I will recall a little bit of notation. From now on, A will always be a finite subset of real numbers, and we'll think of A as being ordered in the usual ordering. Strictly speaking, we probably should be thinking of A as being a sequence, but that's a distinction I'm going to abuse throughout the talk. And its sumset and product set are defined as, let me just get set up here, as the set of all pairwise sums of elements of A and the set of all pairwise products of elements of A. Two sets which in cardinality are bounded by the size of A squared. And of particular interest to us in this talk is the k-fold sumset, or the iterated sumset, which comes from taking sums of k elements chosen from A. So this guy here. All right. So a lot of problems in number theory concern the way in which addition and multiplication interact. And a lot of statements tell us that they interact like oil and water. One such statement is the Erdos-Szemeredi conjecture, the sum product problem, which is a more combinatorially flavored statement. And it's an uncertainty principle, which says that essentially any set of rational numbers, any finite set of rational numbers, has either a sumset or a product set, which is nearly as large as possible. So that's the exponent 2 minus epsilon up here. And certainly in the last 25 years, there's been a lot of work about this conjecture. Rather than list, at first when I was writing these slides out, I tried to list all the names and I got, I don't know, to 20 and still was finding ones that I missed. So I'm not going to write them out explicitly, but let's say that a lot of people have worked on it and many of the usual suspects will appear later in this talk. The bound 2 minus epsilon, I think it's safe to say, is currently out of reach. Pretty well out of reach. I don't think that our understanding of the problem is sufficient to get there right now. I think it's going to require some new insight. But you sort of never know with these kinds of things. Someone might make this brilliant, simple observation. It's happened a number of times. It seems to be happening more and more these days, where the right spin on the problem might hand it to us completely. I think Erdos and Szemeredi originally made this conjecture for sets of natural numbers, but the problem is dilation invariant. So you basically get it for rational numbers right away. And I think it's probably true for sets of real numbers, or maybe even sets of complex numbers, but the full exponent 2 for complex numbers is not the sort of thing I would bet my life on. I mean, sometimes you get a feel that there could be some bad algebraic counterexamples or something like that that just need to be discovered. But I don't know. I still think it's probably true for C. I'm just not willing to make a conjecture about that. All right. So this is about the sum set and the product set, but Erdos and Szemeredi went further. They conjectured that, in fact, the growth, by growth I mean undertaking sum sets or undertaking product sets, the growth persists. So that if you take the k-fold sum set or the k-fold product set, one of the two of them should also be nearly as large as possible. So up to some constant that depends on k and epsilon, one of the two should be as large as a to the k minus epsilon, which is as large as the number of variables permits. This problem is harder. I mean, it's obviously harder because k equals 2 is a special case. But I think it's genuinely more difficult because the more sums or products you take, the smoother the sets kind of become. So, you know, one way to think about this is if you were to choose n to the delta random numbers from the interval 1 up to n. And maybe that will grow under sumsets for a few iterations, but once you take more than, say, 1 over delta sumsets, then there's kind of no room to grow left. So they sort of fill out an interval. This set will sort of fill out an interval, and then its growth will decrease. It will start to slow. So to prove a conjecture like this about iterated growth, you somehow need to observe that either sums or products have a sort of non-smoothing property. And to some extent, that's what this talk is about a sufficient condition to be non-smoothing. By the way, throughout this talk, feel free to ask any questions and pause me.
I have a question about the theorem you were just showing, or the conjecture you were just showing. So what's the best thing known for this? Like,
I think
how does
it'll come up on the next slide.
Oh, perfect, great. So
this is, I've made this, it's somewhat qualitative.
It basically, so a major breakthrough in the area was from the early 2000s, I think about 2003. And it said that you will always have persistent growth, but it does not, I mean, you can read off a relationship between L and K. So the theorem was due to Bourgain and Chang, and it said, if you give me an exponent K, I will return to you an integer L, such that if you take L sums or L products of elements of A, one of the two of them will produce size of A to the K distinct numbers. So the exponent of growth can be as large as you want, but you need to use potentially many sums or many products. This is a theorem about finite sets of rational numbers. There are variations on the sum product problem. Basically, within reason, any kind of expression which involves some mingling of addition and multiplication should produce similar phenomena. And so with Ollie and Dmitry Zhelezov, we proved a theorem about products and shifted products. Basically, any set that has few products will have their multiplicative structure destroyed by introducing a translation. And again, that is a theorem that holds for subsets of Q. But we expect the Erdos and Szemeredi conjecture to hold for subsets of R. So what gives? Well, the technique introduced by Bourgain and Chang, which builds off of a really beautiful Fourier analytic idea of Mei-Su Chang from a few years earlier, relies on unique factorization. And there are ways of introducing unique factorization using ideas from transcendence theory. You know, you could probably reduce problems about some product from R to the algebraic numbers. But basically you would need something that is kind of uniform in the degree of the extension or something like that. It's not a big deal, I'm not going to get into it, but there's some hard number theory that will come into it, and even with the hardest number theory we know, there are some open problems in additive combinatorics, things like polynomial Freiman-Ruzha, which are going to get in the way. So carrying the ideas of Bourgain and Chang over to the real numbers seems like it's a bit of a way off. So this talk is about finding continued growth through a different method. This time it's going to be convexity. Okay,
So let's give some history on that problem. A set or sequence A is called convex if its sequence of first differences, so that's numbers of the form AI plus 1 minus AI, is strictly monotone. And in fact, I'll probably reduce to strictly increasing, although decreasing is fine. It's just, I don't want to create a lot of confusion by switching between the two. So I'll probably just pretend that it's always going to be strictly increasing. So strictly increasing gaps between consecutive elements of my sequence. And there are some set conjectures about convex sequences. Erdos conjectured that for any convex finite subset A in the reals, the size of the sumset of A is significantly larger than the size of A. He probably conjectured that it's nearly as large as it could be, namely the size of the sumset is quadratic in the size of A, or nearly quadratic in the size of A. Off the top of my head, I don't know if that's what he conjectured. Anyways, in this form, the conjecture was resolved by Hegivari in the 80s, I think. Not in such a strong quantitative way, but certainly in the qualitative sense. And then after Alekesh introduced combinatorial geometry to the sum product universe in the late 90s, Alekesh, Nathanson, and Ruzha proved a strong quantitative form of Erdős's conjecture, that the sum set of a convex set A with itself is larger than the size of A by a square root factor. So A to the 3 halves. And then there's been some subsequent work on this, notably by Schoen and Skredov, and the current record is also from the spring, due to Rudnev and Sophie Stevens. And they get the exponent 1 plus 11 over 19. I think that's still the record. Sometimes a month will go by and the record will have changed hands more than once in this area. Okay. So I'm going to spend some time talking about this Alekesh, Nathanson, and Ruzha statement because actually they proved a lot more. So here's not the most general version of their theorem, but the one that I'm thinking about throughout this talk, which is not about convex sequences, but about convex functions. So if f is a convex function, which you can think of as monotone first derivative, and A is any set of real numbers satisfying a doubling condition, A plus A is smaller than K times A, then the image of A under F will have substantially larger sumset. It will be bigger than A to the 3 halves divided by the doubling constant. So another way of thinking about this is that if you start with an additively structured set of numbers, A, so K is not too big, then that structure will be disrupted by passing A through a convex function. The resulting set will have much larger doubling constant. So one corollary of this is the theorem that was on the previous page, that any convex sequence has large sumset, because any convex sequence can be thought of as a convex function applied to the first n integers, or first n natural numbers. And that set has doubling 2, basically. So K would be constant. And you would get the size of A plus A is larger than A to the 3 halves. Getting back to the Erdos-Szemeredi conjecture, if A has small doubling and you take f to be the logarithm function, then you will conclude that the set of logarithms of A has large doubling, but that is only a hop away from the product set of A, not even a skip and a jump. So if A has small sumset, then A will have large product set. And this recovers the sum product exponent of 5/4 that Alekesh had proved. All right. So convexity is certainly related to the sum product problem. And that was our line of attack. The proof of Alekesh, Nathanson, and Ruja used the Szemeredi-Trotter theorem that has become standard in the area. But in the last year and a half or so, Ruja, George Shakin, Joseph Shoimoshi, and Szemeredi proved the following theorem, which I'll call the R Triple S Theorem, to spare myself a tongue twister. And it says that if A is a convex sequence, then the set A plus A minus A is quadratic in size. So if you give yourself an extra variable, you jump from 3/2 to 2 in the exponent. And what's amazing about this proof, well, two things. One is that it's completely elementary. I will show it to you. It's remarkably simple, and it's also sharp. So if you were to take the first n squares, then basically because there's no room to grow, the set A plus A minus A would have the size of A squared. So, so you can't really do better than this, as stated. One thing worth noting, though, is the squares is a convex sequence of integers. They form a convex sequence of integers, but they are the least convex sequence of integers because the gaps in a convex sequence need to be distinct. And somehow there aren't that many distinct integers. So squares are, in a way, the least convex sequence of integers, which are still convex. Okay, so my plan now is to show you the proof of this quadratic result. Basically, what we're going to do is squeeze the expression AI plus AJ plus 1 minus AJ between AI and AI plus 1. Each expression of this form belongs to A plus A minus A. And as long as J is smaller than I, this gap here, AJ plus 1 minus AJ, will not be able to push AI out of the interval because it's smaller than the gap between AI and AI plus 1. So you could view this, you could prove this, in a second, just by writing down the inequalities, but it's a little bit nicer to think about it pictorially. So what it really comes down to is if I look at the gap, the space between A1 and A2, I can squeeze that same space into the interval that follows it, and into the interval that follows that, and into the interval that follows that. If I look at the gap between A2 and A3, I can squeeze that same gap into the interval between A3 and A4, and the interval between A4 and A5. Let's do this one more time. If I look at the gap between A3 and A4, I can squeeze that same gap between A4 and A5. And so there's 2 new elements. There's 3 more. And there's 3 more again. And so the result of doing this is that you manage to squeeze I elements of A plus A minus A into the ith interval. And of course, these intervals are disjoint because they're just the intervals between consecutive elements of your sequence. So if you've produced I elements in the ith interval of your sequence, then altogether you've produced the sum from I equals 1 to n minus 1 of I, many elements, and that's the size of A squared. And that's all there is to it.
So in fact, the constant is just a half, essentially. Okay. So our theorems are basically the result of trying to push this idea as hard as we could. And one of the ways of pushing this idea is to iterate it. And because of that, I'm going to now say that a sequence is one convex if it's convex, and inductively say that A is k-convex if its sequence of first differences is k-1 convex. So for instance, the first n squares are 1 convex. The first n cubes are 2 convex. And any exponential sequence would be k-convex for every k. For every k that makes sense. So k up to n. So this is really just a measure of how fast the sequence is growing. Okay, so now that we have our notation, the first theorem, which is sort of the model case, says that if A is a k-convex sequence, and you take enough sums and differences, 2 to the k sums, and subtract 2 to the k-1 elements of A, then the result will be size of A to the k plus 1 divided by 2 to the k squared. So just to highlight the dependence on the level of convexity here. I think the right way to think about this is to take little k fixed. I mean, it could be large, but one shouldn't think of it as going to infinity. So really what this is a theorem is about is achieving size of A to the k plus 1 as a lower bound. And for instance, if you were to take the cubes now, you would get 4 copies of A minus 3 copies of A is bigger than the size of A cubed. So you get unlimited growth with enough sums and differences. The second theorem is the Alekesh-Nathanson-Ruzha take on the first theorem. So instead of a convex sequence, it concerns an arbitrary set with some sort of doubling condition and a convex function. So this time we're going to ask our function to be not just convex, but super convex in the sense that we would like f and its first k-1 derivatives to be strictly monotone on some interval. And then you take an arbitrary finite subset of that interval satisfying, I'm going to call this a tripling condition, even though that's not really what it is. Satisfying A plus A minus A is smaller than k times A. And then if you take enough copies of f of A and subtract enough copies of f of A from it, then you get a lower bound of the form A to the k plus 1 with some dependence on the parameter capital K, that was the sort of tripling condition, and some logarithmic terms. Again, the way this theorem should be thought of probably is with little k being fixed. So you fix some level of convexity. Then if you take capital K to be sufficiently small and enough copies of A to take sums and differences from, you get a lower bound of the form size of A to the little k plus 1. So this is an estimate that's a similar shape to what we had before for convex in theorem 1 for convex sequences. So a few words about this theorem. Basically, it shows that any f, which is not a low degree polynomial, because eventually a low degree polynomial, if you take enough derivatives of it, not only is it not monotone, it's constant, it's identically 0. And it's not wildly oscillatory. Any function which is well behaved in that sense has to destroy additive structure, which is, I'm sure, a familiar idea to most everyone here. By considering, say, the polynomial x to the k, x to the little k, which is convex of the right order, there's certainly no beating the lower bound in this aspect, size of a to the k plus 1. The kth powers will grow until you hit that bound and then stop growing. As is pretty common in this area, the dependence on capital K, this tripling constant, is sort of nasty. This dependence is sort of the same dependence you would get if you looked for a hypercube, or a Hilbert cube rather, in a set with doubling K. And that sort of comes out of the proof. Unfortunately, the method so far does not give a Bourgain chain type result because we have to assume something on a plus a minus a. So if you said that 3a minus a was small, then we would be in trouble. I think we're optimistic that the ideas could be pushed maybe to deal with something like that, but we haven't managed to do it yet. All right. So the plan for the rest of the talk is that I'm going to sketch the proof of theorem 1, which is the model case. And that will introduce the kind of iteration scheme that we're going to use. And then I'm going to prove theorem 2, which is the kind of Alekesh, Nathanson, Ruja variation of the trick when k equals 1. So that will serve as the base case for the iteration. And then if you believed how iteration worked in the model case, you will probably be convinced that the same or similar iteration would work in the more general case of a convex function. Okay, so let's remember what we're trying to prove in theorem 1, that 2 to the k copies of a minus 2 to the k minus 1 copies of a produces size of a to the k plus 1 elements modulo some constant that depends on k. If you think back to the R Triple S trick, it was to sandwich a number of the form ai plus aj plus 1 minus aj in between consecutive elements of the sequence. And this aj plus 1 minus aj expression is a term of the first difference sequence, which is itself convex, or convex of one level less if we're dealing with a larger value of k. So I've got a sequence which is convex and has I different terms in it. And so basically, I'm ripe to iterate the trick. So all that you need to be concerned with is that when you apply this trick, you stay within the interval you started with. That's going to maintain disjointness. And that every time I apply the trick, the level of convexity decreases by 1, which means I can get away with applying this trick up to k times. So for instance, if I applied the trick to this new sequence, so these elements belong to the set A. Well, when I apply the trick, these elements belong to delta A. And when I apply the trick to this sequence, everything's shifted by AI. And then I'm going to take some expression from delta A plus some expression from delta A and subtract some expression from delta A. And so the resulting sequence will belong to A plus A minus A plus A minus A plus A minus A, which works out to 4 copies of A minus 3 copies of A. And this new sequence, if I set up the induction right, will be convex of one level less, so I can iterate again and again and again. And every time I do, I basically pick up a power of I. When I go to count my elements, I pick up a power of I, So I will be something like sum of I to the k, which will produce size of a to the k plus 1. So for instance, this sequence has I elements, and in between AI and AI plus 1. And when I apply the trick to it, it's going to square that. So just applying it twice, I will get the sum of I squared, which is going to produce size of a cubed at the end. And once you believe that, doing it k times will behave similarly, and I'll get an a to the k plus 1. Okay, so this shows how the trick is ripe for iteration. Now I'm going to focus on how to pass from sequences to the image of a set with this tripling condition under a convex function. Okay. So in the base case, when k equals 1, the statement we're trying to prove is that if a plus a minus a is smaller than k times a, then f of a plus f of a minus f of a is bigger than a squared divided by k times log a cubed. I'm not really going to put the emphasis on logarithms here. I'm actually going to pretend that logarithms are constants and forget about them completely. The basic idea of the argument is that consecutive differences, when you're looking at a convex sequence, look like some differenced version of the function. So if I really did have a function applied to an interval and that was dealing with a convex sequence, then the gap between two elements of my sequence would just be f of n plus 1 minus f of n. And so motivated by that, we'll define the differenced function f sub h of x to be f of x plus h minus f of x. So if f had however many monotone derivatives, then the difference function has has one fewer monotone derivative. If f is convex, then this is monotone. So that's this first bullet point here. F sub h is monotone, as are the first k minus 1. I think that's probably a k minus 2 derivatives. And more importantly, if you have two consecutive elements of the set A which differ by h, so that an plus 1 is an plus h, then f sub h applied to an, well, what is that? That's f of an plus h minus f of an. And this is really just an plus 1. So it belongs to f of a minus f of a. So those are the two important points. So we're going to set h of a to be the set of consecutive differences from elements of the set A, which satisfies some tripling condition. And we're going to set m to be the cardinality of this set of consecutive differences. And for any consecutive difference h, we will denote by r of h the number of representations of h as a consecutive difference. So that's the number of n, so that an plus 1 minus an is equal to h. And after a dyadic pigeonholing argument, we can further assume that this function, this representation function r of h is roughly constant. Let's say it's equal to r. And there are
capital N, or size of A, many consecutive differences coming from my set, but they're not all distinct. However, if they all have the same number of representations and the number of distinct consecutive differences is M, then the representation function will be about size of A over M. Okay, so each consecutive difference is realized about size of A divided by M times. Okay, so we're going to apply the R Triple S trick again. So we order the set of consecutive differences. H1 is smaller than so on, HM. And if I have a pair, AI plus 1 minus AI, which has gap H sub M, then I can squeeze any of the smaller gaps in between AI and AI plus 1. This is the very same trick, because I'm adding something here which is less than HM to AI, which means it's not going to catch up to AI plus 1, because the gap between AI plus 1 and AI is bigger than HJ. And for each pair of elements of A that have HM as that gap, I can perform this trick independently, because I'm sandwiching these gaps between consecutive elements with difference HM. So I do this independently for each realization of HM as a consecutive difference. And then I do this for every M separately. So in doing so, I've produced M elements of A plus A minus A between any two elements with gap HM. And there are R such elements. So all told, I get R times M squared, which is about the size of A times M, distinct elements from A plus A minus A. So I have the lower bound, size of A times M, less than the size of A plus A minus A. But I put a tripling condition on A. So up to logarithms, M is smaller than K. All right, so where does the function come in? Well, because F is convex, I cannot have a simultaneous additive quadruple between consecutive elements on the A side and on the F of A side. I cannot have AN plus 1 minus AN equal to AN prime plus 1 minus AN prime, as well as the same thing, but after applying F. So any pair of consecutive elements with the same gap on the A side, or rather, if I look at all of the pairs of consecutive elements with a fixed gap on the A side and apply F to that set of pairs, now I get a new set with distinct consecutive gaps. In other words, if I set A sub H to be the set of all elements from the A side with gap H, then I apply F to all of these elements, then the intervals from F of AN to F of AN plus H, those intervals all have distinct lengths. Once again, we're ripe to apply the R Triple S trick. So I do that on the F side independently for each H. So I fix an H, I look at all of the consecutive pairs with gap H on the A side. I apply F, and now all of those intervals are disjoint and they have distinct lengths. And when I apply the R Triple S trick, I'm going to produce about R squared sums belonging to those intervals. So as a result, I'm going to produce R squared M elements of F of A plus F of A minus F of A. And the estimate that I had established previously, that M was smaller than K, comes in. So R squared M is larger than R squared M squared over K, and Rm is the size of A. So we get this estimate, which is up to logarithms, what we were looking for. Hence this is hiding the logarithms. And those just came out of the dyadic pigeonholing. Okay, so this basically gives us the base case of our induction, and we will iterate this procedure as we did in the model case. And really all it comes down to making this iteration work is to notice that the sums I produced on the F side will look like this: F of AI plus F of JA plus H minus F of AJ. And I could rewrite that as F of AI plus F sub H of AJ. And this is a function of one level of convexity less applied to the sequence of AJs, which was the sequence coming from elements of A with a fixed gap, H. And that's really all it takes to, apart from some tedious bookkeeping, to prove the theorem. And I think I have come through mercifully under time. So I'll stop there.